So let's continue with functional groups. Now, you probably stopped, had a coffee, so that's great. So we'll continue here. So let's have a look at something else with carbon and nitrogen in. Okay. This is a nitrile. Okay. It is a carbon attached to a nitrogen. Now, if we look closely, that is a triple bond. Okay. There are three bonds between the carbon and nitrogen, but that's a nitrogen functionality. Okay, don't confuse that with Cn minus, which is cyanide. Okay, it's not toxic. Nitriles are not toxic. Cyanide, we know is toxic. So, subtle but important difference because this nitrile is often referred to as a cyano group. So we have to be aware to make sure the distinction between cyano and cyanide, but it does have a triple bond. Okay. On the other side over here, we have what's called an imine. Now, imines can be carbon chains with nitrogens attached to hydrogens, or you may get double bonds with other carbons attached, and then we now have what's called an enamine. Okay. But I want to point out to you that we can have double bonds to nitrogen and triple bonds to nitrogen with carbons. So that's our nitrogen groups. Now, let's look back at oxygen. We've already looked at alcohols, but the next extension of that is to add an ether. And if you look closely at an ether, we have a carbon chain and a carbon chain with an oxygen in the middle. So if you break that down, we'll go back to this compound, which I drew in blue because this is water. And if we replace one of the hydrogens, guess what? That's called an alcohol. And if we replace both hydrogens, we get an ether. So that's all we're doing is replacing bonds, replacing hydrogens with carbons. An alcohol has one carbon chain and an oxygen, and ether has two carbon chains with the oxygen in between. And if we're looking closely, we'll say, wait, that's a primary alcohol. I remember that from an earlier lecture. Fantastic. And then subtle differences is we can have this versus this. And here you can see the carbon chains on either side are the same, so we're going to call that a symmetrical ether. And then this must be an unsymmetrical ether because the groups on either side are not the same. Does that help? Now, if we look closely at our periodic table, below oxygen is sulfur, and we know elements in the same family undergo very similar reactions. So let's just introduce some sulfur derivatives. This is called a thiol, and thiols are known to have very strong smells. These are the ones that are used to make natural gas smell, so we can detect it. That's a thiol, which stinks. This is a sulfide, obviously two alkyl groups attached to the sulfur. In addition to the sulfide, I know you know what this is going to be called. This is a disulfide because it's got two sulfurs attached. And because we put the disulfide in there, I'm going to go back to the oxygen like so, and I'll put this in the side group. You know that in the parentheses there, this is hydrogen peroxide, and it's a peroxy group because it's got an oxygen-oxygen bond. This is a peroxide. Oxygen-oxygen bond. They're not very stable. They're somewhat explosive, but just want to introduce that to you. So if that's a disulfide, I'm obviously going to put this in, and you're going to say, well, does that really exist? Well, yes, it does. These trisulfides are found in onions, just like the disulfides and the sulfides. And we know that once we cut the onion up, it begins to oxidize. That's what causes the lacrimator, which causes our eyes to water. So that's a trisulfide. Okay, so try to stay on focus here. Now, if we look at our periodic table, we know a lot of properties about carbon molecules. And in particular, we also know about sulfur. Sulfur is lower in the periodic table, and it's able to hybridize its s, p, and d orbitals. And if it's got empty orbitals, it wants electrons, right? If it's got orbitals, we want to fill it with electrons. Just like if we have an empty bank account, fill it with someone else's money. So we're going to want electrons. So because of that, sulfur is able to form 4 bonds and also 6 bonds. So sulfur is unique in that we form 2, 4, or 6 bonds. And the reason for these higher level bonding, 4 and 6, is because it can accept electrons. It's lower in its periodic table, therefore it has access to its higher orbitals, and so it will accept electrons from oxygen to form this, which is a sulfoxide, and this, which is a sulfone. Okay, and I'm going to write the sulfone out like this, because depending on which textbook or which website or which Google app you use, may appear differently, but this is also a sulfone. So there you have those sulfur derivatives. And then finally, at the bottom of the page, I'm going to draw this. Now, this on its own is benzene. Okay, it's a 6-membered ring, formula C6H6. It's got alternating double, single, double, single, double, single bonds around the ring. And we can draw that this way, or we can draw it that way, depending on where the double bonds are. Okay, and this is an example of an aromatic or aryl or arene group. Okay, so benzene is an example. This is a specific compound called benzene, but if I then put a substituent on it, I guess then we can call it an aromatic or arene group, which requires this alternating set of double bonds